Welcome back, all of you. In the last class, we discussed about polarization transfer technique, especially for the heteronuclear coupled spin system. Starting from the basics, we understood what happens if there is a selective saturation of a particular transition. Like I take a particular transition and selectively I saturate that, make the population between these two energy states equal. Then we saw, especially if you do the proton transition, we saw enormous change in the intensity of the carbon-13. Same thing we observed when you do the population inversion also. Of course, this is analogous even to the homonuclear case also we observed. And then we found out when this thing happened, the intensity of the carbon-13 J-split doublet, they will be antiphase character. One is with minus intensity 3, other is plus 5. Now immediately after the polarization transfer if takes place, we design an experiment. Let us say I select a carbon-13 or take a proton channel, apply a soft pulse for a selective excitation. Then after I also apply carbon-13 hard pulse and start collecting the signal. And while if you want to do the decoupling, we saw that the antiphase character of the carbon-13 doublet is such that minus 3 and plus 5 intensity, and whatever the gain we got because of polarization transfer get nullified. So that is not a happy situation. So what we wanted to do is to overcome this situation. We wanted to introduce what is called a spinnacle-like sequence, where we are going to put 2 180 pulses, one on the carbon-13 channel, one on the proton channel simultaneously. So this will prevent the evolution of the J coupling of the carbon-13. So this is the advantage of that also. And at the same time, we also saw that when you do this spinnacle-like sequence, this antiphase doublet will become in-phase doublet, and especially when you apply a 180 pulse exactly at the center, and the delay between these two is adjusted such that it is equal to 1/4J. Delay between the first pulse and 180, and the second delay between 180 and another pulse should be exactly equal to 1/4J. Then we saw that if that is the situation in this experiment, the antiphase character of the doublet became in phase, and it is possible to do the decoupling. It is a very fantastic thing. So we can incorporate this in varieties of heteronuclide detected 2D experiments. To understand that vectorially, this is what I wanted to discuss today. Let us see the evolution of the magnetization, how it is happening as a during the NFT sequence, just by vector diagram. We will come to the this thing in the product operator later. This is the NFT sequence which we discussed so far. We gave it said this is a proton pulse and one for delay, and you would say 180 pulses, one on carbon-13, one on proton, and then we apply 90 pulse. This is this echo sequence, and then you apply detective pulse here for the carbon, and then start decoupling. This is a very simple experiment. What is going to happen in this INEFT sequence? Of course, INEFT we also discussed in the previous course. Those who want to get more details, you can please refer to that. The evolution of magnetization at the different time of the pulse sequence can be understood. I have identified at different stages of the pulse sequence as A, B, C, D, E, F. Let us see vectorially how the magnetization behaves at these different points. The proton is a doublet due to its coupling with carbon-13, and H alpha and H beta are the doublet components. H alpha and H beta are the doublet components. At A, HA and H beta components, the magnetization are along Z axis and is in equilibrium. Especially at A means here. Here nothing has been done. We have not even applied the pulse. So magnetization is in equilibrium. That's correct. This is what it is. So both the components of the doublet are along the Z axis. So now what we are going to do? Look, let us see at B what is going to happen. We applied a 90-degree hard pulse on the proton channel. And when you apply the 90-degree pulse, what is going to happen? The magnetization flip to Y axis, because it's a 90-degree X pulse. It flipped to Y axis. Okay. We have got alpha and beta components of this flipped here. So that is immediately after 90-degree pulse. That's what is going to happen. Now we have a time t. During this time 1/T, 1/4J, the spin starts evolving. We discussed about evolution of J coupling and then the chemical shift. What happens? How does it evolve with the delay? Everything we discussed. Remember in last 2 classes. Now at C, what is happening? The C delay is exactly 1/4J is given. At C during the first delay, the H alpha and H beta components are rotated by 1/4J. Remember, it is just 1/4J. 1/4J means H alpha is going like this other is like this. One we are going to call this as fast moving and slow moving components. One starts moving like this, other starts moving like this. They are at 1/4j. That's fine. Now what is going to happen? Immediately after that, we are going to apply 180 pulse. 180 pulse on both proton channel and carbon channel we are applying. First let us see what happens if you apply proton channel 180 pulse. What does 180 pulse does? We have been discussing long for quite some time. It inverts the population. So it will invert the population means it will invert alpha and beta components of the doublet. 180 pulse what it does? It inverts the population. That means alpha and beta states gets inverted. And now what is going to happen? Alpha and beta, just alpha came here and beta came here and they continue to move in the same direction. Now, then what is going to happen? We wait for another 4j. After another 4j, this has to refocus. Okay, we will come to that. Before that, let us see what is going to happen. We are also applying the pi pulse on carbon 13. It does not matter whether you are going to apply X pulse or Y pulse. Now what is going to happen? Carbon 13 pi pulse, it inverts the magnetization of carbon 13. See, carbon 13 is still along Z axis. We will not touch that. In the pulse sequence, we are dealing with only with the proton pulse. Please remember, in the pulse sequence here, we are up to this carbon 13 only. We are not even touched. We are only discussing of this only proton pulse. Proton 90 delay and this thing. Now, if you apply carbon 13 here, still magnetization along Z axis. So what is going to happen? It will invert the population. The spins which are along Z will come back to minus Z. This is what happens. So now I am inverting the population. This is before applying the carbon 13 180 pulse. This is the population state. That is what we have been understanding, how the population gets distributed between different energy states. This was the thing we started with before doing anything. Now population after 180 degree pulse, population the carbon 13 gets inverted. Which are the carbon 13 transition? This is the S transition, this is the S transition. See now what is happening? 10 and 8 were there, this get interchanged. 2 and 0 was there here and this get interchanged. Population of the carbon 13 spins get from plus Z it became minus Z and undergoes inversion of the population between two spin states. That is what is the 180 pulse of carbon 13 do. So when it inverts the levels also population. Now what is going to happen? H alpha component arranged into C alpha component becomes now H beta. Remember H alpha and T, if you consider the doublet of the carbon 13, one correspond doublet correspond to H carbon 13 sees proton in the H alpha state, proton in the alpha state. This one comes sees the proton in the beta state. That was the doublet before applying the 180 pulse. Why the doublet comes? The J coupling we have already discussed a lot. The doublet comes because of this carbon 13 sees proton in two spin states alpha and beta. So now one of the components of the doublet correspond to proton in the alpha state. This I will call it H alpha. This is sees proton in the beta state. This correspond to H beta I will call. Correspond to H alpha and H beta state I get doublet for carbon 13. Okay. So now H alpha component arranging to C alpha becomes H beta and similarly H beta another one becomes H alpha becomes H beta becomes H alpha. So that means fast moving component becomes slow moving and slow moving component becomes fast moving. When you interchange these two, this is what is going to happen. The application of the 180 pulse does something like this on carbon 13. Because the magnetization changed from plus Z to minus Z, the doublet component which is arising because of C alpha and C beta, now C alpha H alpha component becomes C alpha, H alpha component arising due to C alpha becomes H beta and similarly H beta becomes C alpha. Now for slow moving fast moving components get completely interchanged. What is the effect of that now? It means the labeling of the spin states of alpha and beta of proton changed. Alpha if I say this is the alpha state of proton, this is the beta state, now they got interchanged. Now this became beta state and this became alpha state. So now what will happen? They continue to move in the opposite direction. Earlier if you apply one proton 180 pulse only just which change from one axis to other axis, just inverted that, but we did not invert the population. So it was continuing to move in the same direction. But now because of the carbon 13 alpha has become beta, beta has become alpha, those start moving in the opposite direction. That's what is going to happen. So far, carbon 13 was still along the z axis, but we have only applied 180 pulse and then brought from plus z to minus z. But that effect is seen on the proton. Very interesting thing, right? How alpha and beta component of the proton got interchanged because of application of 180 pulse of the carbon 13. This is what it is. Now, spins continue to move in the opposite direction because of interchange of alpha and beta component. Now, wait for the time, another time, which is equal to 1 over 4j. Now, what is going to happen? They start moving opposite like this. See, very interesting thing you must understand. We started like this. After 1 over 4j, it was like this. And then we applied the proton 180. This came like this and this came here. So, they were like this and started moving like the same direction. But now carbon 13 180 pulse did something for this. This became here, this became here. This was H alpha, let us say. This was H beta. Now they interchange. So because they interchange, they start moving in the opposite direction. So now what has happened? Instead of moving this direction, both moving in this direction, this starts moving this way, this starts moving this way. Very interesting thing will happen. It is going to happen now at E. After evolution for 1 over 4j, this spins component again acquire antiphase character. H alpha and H beta, they will be again, this will come here and this will come here. So they get antiphase character. But remember, the spin components of this H alpha and H beta are still in the xy plane. Okay. Now exactly after for this delay, we ensured the spins become antiphase in character. The doublet component become antiphase in character. Fine. Now what is going to happen? We apply a proton 90 pulse. What is going to do proton 90 pulse? Spins are the magnetization still in the xy plane. Then it rotates in the xy plane. The H1 pulse rotates the xy component. Now H alpha components, what it will do? It will take back to z axis. What it will do for the H beta component? It will take back to minus z axis. Remember, I told you about the pulse phase and the receiver phase. When I was talking about the pulse phase, I showed you what happens if I apply a pulse along plus x, what happens if I apply a pulse along minus x, what happens, how the magnetization can be made to tune according to the phase of the pulses we apply. So now exactly what we are trying to do by applying a proton 90-degree pulse. Now H alpha component is taken to plus z axis here and H beta component is taken to minus z axis. That is what happens. So they moved backwards like this in the opposite direction, and population between states 1 and 2 get interchanged. This is a very interesting thing happened, right? We started with this thing because alpha and beta spin states get interchanged. The population difference between spin states of proton 1 and 2, between states 1 and 2 get interchanged. So now population between 1 and 2 is the proton state, the proton transition. Now interchanging that. So this 2 will come here, 8 will come here. This is the diagrammatically you can see what is happening. This is before the 90-degree pulse on proton, this is after 90-degree pulse on proton. Very interesting thing happened. What did we do? This is nothing but selective population inversion I was talking. We did this by experimentally by applying. Now up to this we may ensure that carbon 13 spins the C alpha C beta component. Because of that, the H alpha and H beta component corresponding to the proton, they get interchanged, they started moving in the opposite direction, and the 90-degree pulse ensured that H alpha component went to z axis and H beta component went to minus z axis. Very interesting thing happened now. So this is what it is. Now let us calculate the population difference. Obviously this gain what we saw. So at F, the transitions have population difference of minus 6 and 10. You can calculate here. Population difference between S, this is minus 6 and this is 10. That's what we observed. Minus 3 and 5 plus 5 is exactly the same ratio we got now. So population of carbon 13 at this stage is going to be minus 3 and plus 5 at F. Now till now we have been talking only about the proton. Carbon 13 180 only for interchanging the spin states we did. Now we have to see one more thing. At F, we are also applying 90-degree pulse on the carbon 13. What does that do? The carbon 13 90 pulse creates antiphase transverse components that are detectable. Okay. So now, so far the components along z axis, you can't detect that, but you have to bring it back to xy plane to detect, because z component is not, we are not detecting, right. So what you have to do is apply 90° carbon 13 pulse for detecting the signal, and now we are going to get both this component minus 3 and plus 5, again antiphase character was retained, and we are going to get the signal in the xy plane. Very interesting thing happened now. But again the same problem. Components of the doublet are antiphase with intensity minus 3 and 5, like what we saw in the heteronuclear polarization transfer, especially for population inversion and special selective population transfer. We observed this thing. This means you cannot do the decoupling, because minus 3 and plus 5, if you do the decoupling, you will get only plus 2. Whatever the gain you got is lost. It is of no use. So instead of cancelling the intensity, what we have to do is we have to somehow make sure that we need to get the signal. We will do that. That how we have to do. We will have to give a certain delay and do that. Before that, there is one more question we have to answer. What about the natural abundance carbon 13? We can look for the carbon 13 signal also is present. That also we cannot ignore. We have to suppress that. That is also present. What natural abundant carbon is also present. If before, in addition to polarization transfer, carbon 13 signal from natural abundance carbon is also present. We have to suppress that. How do you do that? There are ways of doing it. What to do is we have to do two experiments. The last proton pulse, once you do plus 90, apply along 90 y axis plus 90, other is apply along minus 90, minus y, plus y and minus y axis you have to apply both 90° pulses. 90° plus y pulse, 90° minus y pulse you apply, then coord the data. Let us see what is going to happen. At f, just before proton pulse, this is what we observed. Alpha and beta components are antiphase in character. Now we applied proton 90 pulse and we took the magnetization alpha component to z, beta component to minus z. That is what we observed. At f, now carbon 13 90 pulse, this is what we got for the plus y. Now after carbon 13 90 pulse also, this is the thing we observed. This is exactly what we were discussing till now. This is our plus y pulse. Remember, proton pulse and carbon 13 pulse we saw it was plus y. Now let this be same, we are not touching that, and here instead of proton plus 90y we apply minus 90y. See what is going to happen. Now what is going to happen now? Alpha component came here, beta component came here, because it is a minus 90 y along y axis we are applying. Phase of the pulse is 90 minus y now. Now what is going to happen? It will start continuing like this. Now this will become minus 3, this will become plus 5, and when you do this, when you apply the carbon 13 90 pulse, now this will become, this minus 3 comes here and plus 5 comes here. What happened? In one experiment the minus 3 component was here, plus component was along plus y axis. In other experiment when you apply minus y pulse, plus 5 came along this axis and minus 3 came along this axis. Both are opposite to each other, right. Now what we will do is, now this is the component of the intensity of this thing, minus 3 and plus 5 is the components of this 90° plus y pulse. Now what happens if I take for minus y, exactly we saw this was interchanged. This became plus 5 and this became minus 5. That is what I showed in the vector diagram. When you apply, instead of plus y pulse, if you apply minus 5 pulse, these two components interchange, that is all, nothing happened. This became plus 5, this became minus 3. Now both the experiment you do, in both the experiment, natural abundant carbon 13 signal is always a constant phase. That is not getting changed. That remains same with always the constant phase. Okay. Now what we do is we can add or subtract. Let us see. Subtract experiment 1 with experiment 2. What is going to happen now? If you take this difference, okay, you take this difference now. One experiment 1 with experiment 2. Here nothing is going to happen. Come back here. Let us calculate the net intensity of the each transition mathematically. When you do the subtraction, remember here, never add it up. If you add it up, you are going to have a difference in the intensity, because this is minus 3, this is plus 5, we will get 2. But I am subtracting minus 3 and then it will become minus 5, it will become minus 8, I am subtracting. So when I do the subtraction, this minus 3 minus 5, this will become minus 8. Similarly, other component plus 5 minus of minus 3 is equal to plus 8. So what did we do? We got the gain in the intensity of the signal, and antiphase character, everything whatever is there, we can take care of this one. But natural abundance carbon 13 will give a constant signal in both the experiment. This experiment what we did to ensure, if you do the 2 experiments and subtract this one, then this intensity of the signal will add up. The antiphase character, because of that, nullification of the signal or reduced intensity will not be there. But still natural abundance carbon, what will happen? They will come with the same phase, that is not getting changed. Only here the phase is changing from minus 3 to plus 5 and plus 5 to minus 3. But natural abundance will not get change the phase, it remains same. So now what we can do is, with 90° Y pulse, this is what we get, and this is a natural abundance carbon plus this will both will come. This natural abundance carbon is just 1%, okay, that is not enhanced intensity. Now in the other case, if you apply 90 Y minus Y pulse, again natural abundance remains same and this becomes this. When you subtract, what will happen? Here we got the gain in the intensity, whereas this one, if you subtract with this, this get nullified. So you can subtract the natural abundant signal coming from natural abundant carbon, whereas this will add up. That is the beauty of it. So difference of 2 experiment cancel the signal from the natural abundance carbon and yields only the signal that is transferred from the proton. The magnetization transferred from the proton to carbon, only that signal is detected, and natural abundance carbon signal is completely eliminated. And this is finally we are going to get, and minus 8 and plus 8 is the signal intensity, that gain we are going to get. Okay, so and finally what I am going to show is the signal intensity is how much we are going to gain for different carbons, especially when we are looking at the carbon 13 carbon. Carbon 13 especially CH3, CH2, CH and CO carbons. How the inept helps? Of course, CO carbon there is no proton, we will not worry about it at the moment. We will see only CH3 and CH2 carbon, CH carbon, how the intensity will change. For CH3 it is a triplet, CH2 is a triplet, and in the case of other one, CH it is a doublet with antiphase character. Now here what is happening is the central peak will disappear. In the case of the inept, but this is for CH2. No, I am sorry, not for CH, it is for CH2. CH3, when you do this carbon 13 natural and this is inept, normal carbon 13, 1D carbon 13 spectrum. Now 1:2:1 intensity is there, whereas here with inept this is the ratio which you will see. Because I told you the central peak will not precise, you do not have to worry about it, that is 0 intensity. Only outer component has a change in the intensity which goes by the ratio of the gammas of proton and carbon, and this is the enhanced intensity you are going to get. So minus 8, 0 and plus 8 for the enhanced intensity, and the central peak do not precise and you do not give it any enhancement at all. So I am sorry. Same thing you can look for CH3 group. CH3 group again there is no central component, as I told you, both the 2 components and the higher frequency low frequency move in the opposite direction, and this is the intensity ratio. And if you look at this intensity ratio, the intensity turns out to be minus 12 is to minus 12 is to 12 is to 12. So this is the intensity gain for carbon 13 CH3 group. This is just to show you an example how inept is going to help you. This is an experiment which on a molecule called coumarin, taken from the literature. Here carbon 13 spectrum of this thing coumarin without inept, this is with inept, that is the difference. This is the you see the enhancement intensity because of the inept technique. Of course antiphase character, because this is not a decoupled one, and positive and negative intensity is clearly visible, and you can see there is an enormous gain in this. Look at the noise here and noise here, there is enormous gain in the signal to noise ratio because of inept. Okay. So this is an advantage of inept. especially when you want to observe dilute spin. This is an experiment which is coupled inept, not decoupled. This is a coupled inept actually. Now you can also do the decoupled inept. Do anti-phase character, as I told you. If I try to do the decoupling immediately, is a problem. So what we can do is we can try to do what is called the refocus inept. That's an experiment which will circumvent the problem of anti-phase character of carbon 13 signal, and instead of reduced intensity, then we can make sure that anti-phase character becomes in-phase character, and we are going to get the enhanced intensity. This is the refocus inept pulse sequence. Up to this is clearly known. Okay, up to this we understood. Now what we do is extra delay you are going to give, again like a Spinnaker sequence in the carbon 13, give a time delay here, and then apply 180 pulses on both proton and carbon. After a certain delay, you start collecting the signal. Now what is going to happen? This is the extra additional thing. At the end of the first delay, the doublet component of the CH spin system would have acquired the relative phase difference. There is a phase difference between these things. But 180 pulse on the X nuclei refocuses the chemical shift. 180 pulse on the proton inverts the alpha and beta spin labels of the X vectors. And during the last delay, the two vectors continue to precess clockwise and anti-clockwise and gets refocused along the X axis. Remember, we discussed this about precision, evolution of the J coupling, evolution of the magnetization, how the in-phase character become anti-phase character, and how the in-phase dispersive can become anti-phase dispersive. Everything we discussed in the last two classes. Evolution, that's why evolution of chemical shift and evolution of J coupling I discussed a lot. Without going into the details, I am telling you, the 180 pulse on the X nuclei refocuses the chemical shift, 180 pulse on the proton inverts the alpha and beta state, and as a consequence, during the last delay, these vector components start moving in the continuity process the way it is, and then get refocused along X axis. Then that's what we wanted. The antiphase character, when they get refocused both of them along X axis, there is a gain in intensity. There is no question of nullification at all. That's what happens. After a delay, if you do that, then finally it will come back here. That is what the last 180 pulse, how it behaves, I have shown with a vector diagram. Without going into the details of it, please remember what is going to happen after that. You delay during the time delay, alpha and beta components start moving like this, and then again they get interchanged, and after some time they get overlapped along X axis. Not overlap, refocus along X axis. So decoupler, now we can switch it on and start detecting the carbon 13. You can break the coupling between proton and carbon after this delay. Now the question you may ask me, what is the length of this delay? Because you do not know what is the optimum delay, because the carbon J coupling we should know. It depends upon J coupling, JCH. But JCH for CH3, CH and CH2 are different. How do you optimize this then? What is the right J then? So we have to use delta is equal to 1/2J, which is maximum refocusing for IX for CH. And for CH2 it is 1/4J, and for CH3 it is 1/3J. Then you may ask me a question, do I have to do the 3 different experiments to do this? No, what we can do is a sort of, in principle, you can do the experiment for identifying the carbons. For example, if delta is equal to 1/4J, all carbons appear as positive signal. If I put delta is equal to 1/2J, only CH as positive signals are seen, others are not seen. If I use only 3/4J, then it generates a positive signal for CH and CH3 and negative for CH2. So in fact, if you want to worry about the all positive signal being seen without worrying about which is which, 1/4J, if you use it, you get all the 3 peaks positive in intensity. But you can use this delay and do the experiment for what is called spectral editing. You can identify which is CH carbon, which is CH2 carbon, which is CH3 carbon using an appropriate delay. Use exactly 1/2J for last delta, then you get only CH peaks, all others are not there at all. Then I can identify which are the CH peaks in the complex carbon 13 spectrum. This is an advantage of this thing. So this has been taken from the literature. You see how the intensity of the carbon 13 signal varies in the refocused inept and for different carbons as a function of delay. This is the delay, keeps varying here, and the intensity of the carbon for different CH and CH3 are varied. And look at here, exactly 1/4J, this is 0, all are positive. At exactly 2 by 4J, that is 1 over J, CH2 and CH3 are 0, CH only is seen positive, and exactly 3 by 4J, then these two are positive and CH2 is negative. So you can use this for spectral editing, and this is comparing the sensitivity of the inept with the direct detection of low gamma nuclei. See, this is the carbon 13 spectrum, no NYE, no decoupling, whereas this is the carbon 13 inept spectrum, no decoupling. This is refocus inept again. Of course, still you can do decoupling or not, its choice is yours. And this is a refocus inept with decoupling. And this is a normal carbon 13 spectrum with decoupling and NOE. See the difference now. This is the normal what people observe. When you do the carbon 13 NMR, what you simply do is the decoupling experiment. With the decoupling power is kept on all the time. As a consequence, there will be an enhancement in the signal intensity due to NOE. And this is in spite of that you get this signal. But now if you do refocus enough to get it with the decoupling, and this is the intensity. You see the enhancement intensity. This much gives rise to enormous signal gain and reduce your experimental trial time drastically. That is why in all the heteronuclear experiment of 2D like HSQC, HMBC, etc., we always use polarization transfer technique like INEPT is one of the module which is there in the pulse sequence, and we transfer the magnetization from abundant spin to rare spin or dilute spin and then start collecting the signal. This is not what normally we are going to do, and then of course this we can discuss all those things again and again quite a bit. There is no point in going much more into the detail, but I will just tell you one important thing. DEPT. DEPT is an experiment called distortionless enhancement by polarization transfer. This is used for spectral editing. This distinguishes different carbons like attached proton test, which I did not discuss in this course. I discussed this at touch in the previous course. This is similar to INEPT only, DEPT. Now, DEPT sequence is like this. You can find out from looking at the sequence itself, you can understand there is a polarization transfer that takes place. It is similar to INEPT sequence you can see. Now, depending upon the width of the third pulse here, 5, this we call it as a phi. Now, in this sequence, depending upon what is the last pulse, what is the angle of the last pulse, we can have different type of DEPT experiment called where you can identify only CH carbons, you can identify only CH3 carbon, you can identify only CH3 carbons, analogous to what we saw in the INEPT for different carbons. So, this is the experiment called DEPT, distortionless enhancement in polarization transfer. Again you can see here, when you do the last pulse 45 degree, it is called depth 45. You can see that what you are going to observe, this is positive, this is positive, this is positive. When you are going to do depth 40, this especially the CH2 is 0, CH3 is negative and CH is positive. When you go to depth 135, then this is positive and this is negative. So, now you can use different type of depth experiment. Depth is a simple similar to INEPT like sequence which we saw, but there is a difference in understanding the behavior of magnetization, especially if you consider the last pulse, flip angle of the pulse, the angle of by which you tilt the magnetization by the last pulse, we can vary. It can last pulse can be 45 degree, 90 degree, 135. Accordingly, different carbons have different intensities. Some are positive, some are negative, some get nullified, some carbon like this. You can use this idea to do what is called the spectral editing in carbon 13. Generally, this is what is used for identifying different carbons. INEPT is used generally for polarization transfer experiment in most of the complex pulse sequences. But in a one dimensional experiment, if you want to try and if you want to see that you want to see the simple carbon 13 spectrum and want to see which carbon is which, then you do not need to go to complicated 2D sequences, etc. Simply do the depth experiment with the different pulse sequences, different pulse angles of the last pulse 45 degree, 90 degree, 135 degree, you can make the identification of all the carbons. And this is an example for a molecule called menthol, where you can see this all the carbons are present here, and now it is only CH carbons, and this depth sequence is only for CH2 and this is for only CH3. How we got it? You know that depth 45, depth 90 and depth 135 if you do, depth 90 you are trying to do, you are observing only CH carbons, depth 135 you see this carbons, this CH carbons are all negative in intensity and CH3s are positive, and you can identify which is which like this. So, this is what is called pulse editing sequences using different, and of course, now you can multiply and subtract different peaks, different spectra you obtain for depth 30, 90 and 45, 90 and 135, and then coordinate the data accordingly. Then you can get only carbon 13 only peaks, CH3 only peaks, and only CH2 peaks. All it is possible to obtain. So, that is what you are going to do, and anyway APT I have not discussed, there is no need to worry about these things, but just I want to tell you both the experiment depth and APT and all these things they use to identify the multiplicity. Nowadays nobody uses APT, do not worry, we have to use only depth experiment to identify different carbons. Always do the 3 experiment depending upon the type of carbon, or 3 or 2 experiment, depth 45, depth 90 and depth 135 for identification, but this contains polarization enhancement already. That is why it is called distortionless enhancement polarization transfer. So, this is what I wanted to do. I will stop here. With this polarization technique I have completely covered, and I explained to you how polarization transfer is very much useful, right from starting from the pulse sequence of polarization transfer for a heteronuclear case, selective population inversion, selective population transfer, etc. Then we got a inept sequence, like how we got first a simple sequence and then brought in the spin echo sequence, and then we got into a inept sequence, and how we refocus the antiphase character doublet into the in phase character for doing the decoupling. All those different methodologies, how we can adapt this, we observed that, and we saw that inept depending upon the pulse delay, the last delay delta, you can have different intensity for the CH carbon, CH3 carbon, CH2 carbons. That is one way for using inept for editing the spectrum. And of course, there is a polarization enhancement transfer. As a consequence, there is significant enhancement in signal intensity. We saw for carbon 13 doublet what is the enhancement in signal intensity, for the triplet what is the enhancement, for the CH3 what is the enhancement. For doublet we got 4 times, for CH2 we got 8, and for CH3 we got 12. Of course, you do not need to use any big mathematics, you see, depending upon the number of protons attached, that was the enhancement in signal intensity. Of course, then this is normally not used for spectral editing, it is used for enhancement of signal intensity in the 2D experiments. Depth I showed you is a simple polarization transfer experiment with last pulse, depending upon the pulse flip angle of the last pulse, 40 degree, 45 degree, 90 degree, 135 degree depth experiments you can use to identify different carbon based on their intensity, whether it is positive or negative, based on the signal phases, positive phase, negative phase, or in one case completely one of them get nullified. So, this is what I wanted to discuss in the polarization transfer techniques. Next we will go to a different topic. I hope I gave you the gist of something which we use in 2D experiments. Thank you.